class, which was once you reconstruct the attractor using the late coordinates, for instance, or you can also use the derivative of the variable. There are many ways to reconstruct the attractor. You can also use, for instance, the Hilbert transform and get the orthogonal, the perpendicular component. So from one scalar time series, you end up with some 2 or more variables, and you have the two-dimensional attractor or three-dimensional or whatever. So from that, you can calculate the Lyapunov exponents and the dimension. I don't want to go into details on how to calculate the Lyapunov exponents, but there are programs available for you to look, and you can also look here on how to do this. Basically, the idea is to choose initial conditions near to your points of interest, let them evolve. They will somehow become some ellipse, and that will give you the averaging over time, and it will give you the Lyapunov exponent. So there is one simple approach. To calculate more than one is a bit more difficult because you need to, at each point, recalculate the orthogonal directions. But if you just want the largest Lyapunov exponent, you just use initial distance and let it evolve after a certain time, calculate the distance after a while, and then you can calculate this expression that gives the local maximum Lyapunov exponent. And then you can average over the attractor and obtain a value. And this is a reference. It's pretty old, but it's still one of very popular way to calculate Lyapunov exponents. And then the question is, what does it mean? You always get a positive number out of this algorithm, because by definition, you're looking at a distance. This will always be positive. It's difficult that you get a strict 0 or a negative. So you really need to be very careful if your data is experimental, because if you have noisy data, you need to really compare to some system in which you already know what to expect. So that's what we were talking about last class. You need to use appropriate surrogates to check whether the number that you obtained from your Lyapunov calculation makes any sense or not. In particular, if you just use noise, if you try to calculate the Lyapunov exponent just from noise, it will give you a positive number, okay? So what does it mean? Noise and chaos are not the same, and the Lyapunov exponent is not good enough to distinguish. So I recommend you reading this review paper on how to, if you want to do it from observations or experimental data, it's pretty complicated, actually. The other algorithm that is very, very popular on time series analysis is the correlation dimension. And it's a way to detect chaos and also to detect a structure in data. I already talked about the fractal dimension. Remember, you reconstruct the attractor, then you use boxes, and then you calculate how many boxes you need to cover your attractor, and then use smaller and smaller boxes. So that means that the number of boxes will increase, and this is the box counting dimension. But the problem for time series analysis is that this doesn't take into account how popular the different boxes are. Maybe one part of the attractor only has visited very sporadically. It has maybe a couple of points, and other points of the attractor are very dense. Okay, so this box counting algorithm doesn't really take that into account. And then there is this correlation dimension, which is very, as I said, it's a very popular way to compute a fractal dimension. And the idea basically is to count the number of data points that are at a distance from each point. Is of course more complicated. You need to calculate the neighbors and how these neighbors depend on the distance that you take. And there are other ways based on information theory that I will talk today. Okay, so that was the hands exercise that I left from last class. And now we are going to go into a different set of methods, maybe you don't know, you're not so familiar with, that have been really gaining momentum in the last maybe 20 years. And the first method is the issue of symbolic analysis. So the idea is that if you have a sequence of data points, you can always transform this sequence in a sequence of symbols. In principle, I'm going to put an example from a time series. But don't forget that if you have an image or a matrix, you can always transform. You can always expand this method to analyze that kind of situation. And you need to use a rule that gives you a set of symbols. A simple rule is just to use a threshold. If one value is above the threshold, you can put a 0, and otherwise it's a 1 or whatever. So that gives you a set of an alphabet, different letters with various thresholds. You can have more than 2 letters. And then you can use blocks of letters to define words of patterns. And then you can have a dictionary, which means all these are possible words. That doesn't mean I see them all in my data, but in principle, they could exist. And you can even analyze the language, which is the probability that after D, you have house, or after house, you have yellow, no? That kind of thing. So you can analyze the language of the time series. And for that, you can calculate the probabilities of the different words, if there are missing words because you don't have enough data, or they are forbidden because they're not part of the language. Forbidden means even if you wait long and long, it will not appear. And then you can calculate these transition probabilities. What is the probability that word beta or symbol beta comes after alpha? And you can, with these probabilities, once you have, and this gives you different sets of probabilities, probabilities of words and probabilities of pairs of words coming together, you can calculate a lot of information measures. I just mentioned 2 here, and we will see them a bit later on. So yes, I said this is a threshold rule. You have to choose a threshold. But there's a possibility of having a rule that doesn't need any threshold. You don't need to select any artificial boundary to say this is a A and this is a B. You can just consider the order for data points if 1 point. So this is the example of the threshold rule. No? I'll talk about the other possibility later. This gives you a sequence of zeros and ones, or more in general with other, if you have more thresholds. And then you can consider these blocks of 3 letters. And then your time series can be translated into this sequence of patterns. And this means that depending on the size of the word, the number of patterns will grow pretty fast. And as I said, more thresholds allow you to define more letters. But there is advantages on this because you don't need to reconstruct any attractor. And there are different ways to define a rule, so that might give you different information. But the drawback is that you also have what is known as hyperparameters, the parameters that you need to set in your method, which means in this case, for instance, the threshold or how many letters you consider in your words. And also the fact that if your time series is short, if you want to compute the probabilities, you cannot have very long words, because that means there are many, many possible words. It's impossible to see if one is really a 0 probability, or is that your data is too short and you don't have enough data. The threshold-less rule, which is known as ordinal analysis, it just considers the order in which the data points are in the time series. So let's consider 3 consecutive data points. And then you can see that there are 6 possibilities in terms of how they appear in time. For example, if your numbers are 2, 5, and 7, of course, they can be increasing. There can be some oscillation down, another oscillation down, but then recovers a little bit, okay? And then an oscillation up, another oscillation up, a different pattern, and then go the trend of going down. Of course, this is just for free, but you can do the same, and I will show you examples later. So basically, the idea of this method, again, is to count the probabilities, see how many times these patterns appear in your data. And this allows to take into account the order in which the data appears. And it's also very robust to noise, more than the threshold one, because you don't really take into account this is a 7, or it can be 100, or whatever. You only care if it's higher or lower than the previous value. Okay? The noise will affect only if they are too similar. Or if they are very dissimilar numbers, if noise is not too much, it's not going to change your transformation. Of course, you have to pay a price, which means that the amplitude information, the information of how high or how small these values are, is lost. It's not taken into account. Basically, this means this is just one more tool you can apply to your data, and it will give you some information, but that doesn't mean that it's the same as if you use a threshold, because the threshold it takes into account amplitude information. It's not the same. If your threshold is at 10, then the 7 is below and 70 is above, okay? All right, so what happens if we consider instead of 3, 4, or 5, you can see now that there are many options for this oscillation that we're trying to identify in data. No? These possible oscillations, we have 24. It actually grows at d factorial, so it's 24 or 120. And this is a problem if you don't have a lot of data, because you cannot compute 24 probabilities if you only have 500 data points. No? Well, you'll be quite short, no? Because you need at least 10 data points per bin, 20. Well, maybe you can get away with it, but I don't know. I wouldn't recommend that much. So how to select this hyperparameter that you need to fix to use this technique? Well, it depends, of course, on the length of the data. There's no sense on analyzing long words with many possibilities if you don't have enough data to decide whether this pattern occurs or it does not occur, only because your data is not long enough. And the other is the length of the correlations. So that's also an important consideration. If your data, if these points you don't expect very long correlations, then there's no point in analyzing long patterns, right? And I will go again later on how to overcome, even if there are long correlations, for instance, some time series with a seasonality that we know that things repeat over time every 12 months, there is a way to overcome this without the need of having to consider patterns with 12 letters. What do you do if two values are equal? Well, in general, in real life, the idea that of course, in the logistic map, they will be equal, for sure, okay? But in real life, typically, the observations are always a little bit different. And maybe you record them exactly the same because the resolution of your detection system, your algorithm, your detector, your oscilloscope give you exactly the same number, but it's actually maybe a problem of resolution. So the simple solution to this is to add to one of the values a small random number. Very small, tiny, just to represent that noise that is filtered out by the detection. Okay, so that's a simple way to deal, which is the pattern if I have 5, 7, 7. What would that be, you know? you can just add a random number to this last number and then see what pattern. But that random noise is just a small noise to disentangle this. Okay, so symbolic analysis can be applied to the raw data that you have, to all your data, or you can try to compress, filter, or pre-process the data to only keep the meaningful information. How can you do that? There are many ways. The first is to select the temporal resolution. Let's see this time series. It's a sinusoidal. If you choose one after another, all your data points, what's going to happen? Okay, the trend patterns, which are the 1, 2, 3, or 3, 2, 1, are going to be much more probable than all the others. Because all the others will occur just down here, you have an oscillation. Up here, you have another oscillation. But most of the time, the system is either going up or going down. Okay, so it's trivial. You won't get any useful information. You need to select some lag, and for instance, only consider points that are separated, in this case, for instance, with 9 data points. So you move them, and then you can see that here we have a pattern that goes up, then there is an oscillation, there's a pattern that goes down, then there's another oscillation. This is particularly important also for climate data or any data that has some seasonality. It's not the same if you analyze all the data, consecutive points, that if you, for instance, take one in climate data, you take 1 point every 12, and then you will see phenomena that is the results are completely different. Okay, once you see phenomena that are more associated to weather, and in the other case, you can separate and look at phenomena that are more involved oscillations over several years, and these are more in the climate size. This is a very important advantage of this technique. It allows you to select time scales. I have done, if any of you is interested. Yeah. Broadway. Yeah.
Don't you miss, can't you miss the event that you are looking at?
Exacto, exacto. So that's an excellent question. If we have a roadway, which is an extreme event, with this, can we miss the event that we are looking at? And that is perfectly correct. Now, first, for roadways, you can try this, but keep in mind that you don't take into account amplitude information. So it's important to use something that really detects extreme events. And the other thing I can tell you is that we have applied this method to roadway, and you can see that there is a pattern. I think I'm not sure if I put the slide. I might have it here. There is a pattern that tends to occur before the spike. Okay, so at least you can identify that. But it's true that the roadways are really fast, and this method doesn't really care if it's a roadway or it's a small oscillation. The only thing it cares if it's higher or smaller than the previous value. Okay. But yes, this idea of that you can select the time scale of the analysis is very important. It's very useful because if you apply information measures, we'll talk next class, as mutual information that is computed from probabilities, and you just put the probabilities of all the values, okay, you get some information that is completely different from what you obtain if you just put probabilities of symbols, and the symbols are different if you calculate consecutive data points or you separate them in time. Okay, so that's one way of compressing the data. The other way is to define events, as we already talked about that last class. This issue of defining events and analyzing the sequence of times between events allows to uncover similarities in these two cases, the laser spikes and the neuronal spikes. And these are examples of patterns that you can see here. This has a short time interval, a longer, and then a shorter but longer than the first one. And here we have a different pattern. a small, a long, and the shortest one is at the end. So then what you do is, again, transform this into words and then calculate the frequency, how often one word or another occurs in the data. The third way to compress the data before applying ordinal analysis or symbolic analysis of any type is to use, for instance, a Poincaré map. So you need to choose carefully where the map is. This is an example from a chaotic attractor. You get a Poincaré map, and then you can use these points and define some rule to transform this into symbols. And the last example I want to talk is if you have a data like this, which looks really noisy. This is, again, from a laser, but many of us deal with this type of very noisy-looking data all the time. You can put a threshold and select only the peaks that are above the threshold, which would be those red dots. Okay? So I will later present results in which we compare. What do we see if we analyze all the data? And what do we see if we only analyze these peaks? Sometimes it can be quite different. Okay, so this is a comparison of the two methods. One, you need to define the threshold. The other one, you need to see the order in which the points appear. The advantage, it gives information about the magnitude, but you need to select the threshold. And the number of symbols increases as 2 to the d. In this case, no threshold. It gives information about temporal correlations, because what matters is the order in which these events occur in the data. But this information is lost. And the number of symbols increases like this. So if you compare, this is the important graph, because depending on how much data you have, you can use one method or the other. The ordinal analysis grows with the size of the pattern very high. This is logarithmic scale. So you cannot consider very long words. You know enough data to compute these probabilities. For example, for 6, you need to compute almost 700 probabilities. That means you need at least maybe 15,000 data points. So that's why the threshold transformation can be better. But if the data is very noisy and you only expect correlations between 3 or 4 data points, then it makes sense to use any of them because pretty much are the same. So, okay, so basically the idea is to compute these probabilities. For instance, if you consider patterns of length 3, you have 6 possibilities, as I showed you before. But think about this in general terms, no? You can be using another rule, and you have a different number of possibilities. What do you do? Then you need to do a null hypothesis. The most simple way is to think, well, this time series is noise. If it's noise, then I don't expect any order in the time series. I expect all the patterns to occur with basically the same probability. So all patterns are equally probable, okay? And see, if this is my distribution, then the question is this consistent with the null hypothesis? Okay? So what you do is this type of test in which if at least one of the probabilities is outside the interval I can expect for the uniform distribution, if it's enough that one is outside this interval in which I really detect that there is something in the signal and it's not just random, it's not just noise, okay? So this interval, you can choose variation. For example, if I put a 3 here and I see a probability that is outside this interval of values, I can say, it's like seeing, is this dice a fair dice or not? You throw it many times, you compute probabilities, and then you do this test, okay? Else, we cannot guarantee that the time series is noise. We can only say that we cannot reject the possibility that it's just noise. But we cannot guarantee that it is just noise. I'll show you some examples. So basically, what is this useful for? You can compare real data with model data. You can try to use these probabilities to fit the parameters of your model, try to find the model's parameters that give you best agreement, or you can use it for classification, some other applications, but at the moment I present only these two. As I said before, we have this laser in the lab that has this spiking behavior that is very similar to neuronal behavior, and there are models for neuronal behavior. A simplest one is the circle map. It's a very simple model used for excitable systems. And you can see here that computing the probabilities, 6 patterns, these are 6 different colors, versus some experimental parameter, and changing the parameter of the map, we see similar behavior, qualitatively. I didn't show you the vertical axis, but they are not necessarily the same, particularly because once you start adding noise, then these probabilities become very equal, okay? And if your system model is deterministic, then these probabilities can be quite different, okay? Then the more noise you put, the more equal the probabilities become. You basically lose your signal in the noise. The other example I wanted to talk about, but it's not about this socio-economic complexity, but I find it very interesting too, in an Electro Cardiogram, you can analyze the times between the beats, right? I didn't put the plot here, but you can analyze the time between these beats, and you can again compute probabilities. In this case are patterns with length 4. And if you plot the probability of one pattern versus the probability of another pattern, you can separate people that are controlled with people that have some heart disease. So that's interesting because it's a way of, and it's very robust to noise. If you contaminate the time series with noise, you need to put too much noise to lose these features. Okay, so let's, sorry. Murió. Okay. Yeah. Back online. Let's talk about the logistic map. I already presented this long ago. Okay, so this is the time series of the logistic map. This is very chaotic, almost equal to 4. And if you look at the segment a little inside, if you look in detail, you see this, okay? If you compute the probabilities of patterns with length 3, this is what you get, which you see here that this is missing. Okay, this is actually not missing, it's forbidden. You can extend your time series as much as you want, and you will never see this. Now, maybe this is new to you. If you look at the example I'll show you here, you will see that it always goes down in a single step. It's something that you probably have not noticed ever, in spite of the fact that all of you are very familiar with this map and the bifurcation diagram and blah, 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 right? If you do the histogram, you see that the most probable values are the small ones and the high ones. It's because the system spends quite a lot of time up here, quite a lot of time down here, goes up in steps, oscillates, but whenever it goes down, the next is up. See here, for instance, went down, the next point is up. There are never, ever 3 consecutive decreasing points. Now, this is interesting because it can give you some predictability. In a chaotic system, it's totally unpredictable, but once you know this, and you know that this point went down, you know for sure that the next point is going to be up, okay? This is nice because it's completely forbidden, but there are other cases in which it's not completely forbidden, but there is a different probability. So you get, again, some information about what is going to happen. You don't know how much it's going to go up, but it will go up, okay? So this is the well-known bifurcation diagram that some of you were working before. And this is the new bifurcation diagram, where you change your control parameter, and you see that this red pattern is always forbidden for any values of the control parameter. it's a curiosity, it's interesting, mathematical work has been done, that has been demonstrated. Of course, if this pattern is missing, when you consider d equal to 4, there are many other missings, right? And so on. Okay. Software. I recommend this paper. In the slides, if you press this link, it will take you to my webpage and you can download it because I think this paper is not open access. It has code in Python and also in MATLAB. I just put the code in MATLAB. It's this one. And I want to explain what are the parameters. This code gives you the index. Means that if you're using words of length 4, you have to give 4 values, and it will give you return a number in between 1 and 24. For instance, if you feed the algorithm with 3, 2, 1, minus 2, it will give you a number, or it should give you a number 24. If you feed the algorithm with minus 2, 1, 100, and 2,000, it will give you number 1, and so on. So one of the exercises will be test this algorithm, test its work. And of course, you can use another parameter. So one is the time series, the word length, and then the third one is the lag. You might want to give a long time series and give a lag of 3. So do not consider consecutive points, but return my number using a lag. Okay? So for instance, if you give a pattern like this, it will give you a result that is number 3 because it's pattern here. Okay? It's quite easy to use once you get used to it, and then it's an easy way to analyze your data. All right, so this is a way to extract probabilities from a time series. There are many other ways. I just explained one. And then the question is what to do with these probabilities. The idea is to use a measure that is called entropy. Who is familiar with the concept of entropy, what it means? Some of you, not everybody. Okay? So basically, entropy is a measure of disorder, and it's, of course, related to the amount of information you have. Suppose you're looking for your yellow car. If the situation is like this, you have no information about where you can go and look for the yellow car. But if the situation is like this, then you have the information and you can search for your car here. Okay? So basically, entropy is a measure of disorder and is directly related to the information. And more precisely, entropy was proposed by Shannon. This is the expression. If you have a set of probabilities, or whatever probabilities you have, you calculate the entropy like this, and we can interpret it in the following way. It's the amount of surprise that you should feel if you have the results of some measure. Let me put you a simple example. Let's consider a variable that takes values 0 or 1 with a given probability p. Okay? So the probability of getting a 0 is a p, and the probability of getting a 1 is 1 minus p. Okay? If you calculate the entropy using this, where you only have 2 terms, you have this expression. And this expression you can plot as a function of p. It's a function of p, so p changes between 0 and 1, and this is the plot. In 0.5, the entropy is maximum, and that's because it's your maximum uncertainty. For 0.5, you have no idea what the result is going to be, a 0 or a 1. Okay? All right, so when you use these ordinal probabilities to calculate entropy, that's a magnitude that is called permutation entropy. It's well known for some of you, has been extensively used in the literature of time series analysis, but not only, because you can also transform images. You can also use this method. So basically, you have this time series, you compute your probabilities, and then you calculate the entropy. Okay? Let me give you an example of what you do, what you should see if you use the logistic map. Here is the entropy per number of symbols, and they have used symbol number 6 6 symbol. You can see that basically it behaves similar to the Lyapunov exponent. But it's considerably more simple to calculate than the Lyapunov exponent. And it's very robust to noise. If you add a dynamical noise or you add observational noise, you still have to, you can still calculate, get an idea that the parameter R becomes the system more chaotic just by computing this entropy. It has been used to analyze empirical data, experimental data, from many, many different fields. And I'm just putting here an example on the financial data. I call this, we find a correlation between permutation entropy and economic development and market size. I don't know how significant this correlation or relevant this correlation might have been, but this paper is quite old. I think it's, 10 years ago. You can look at there's been more work on this, or maybe if you're interested, you can find out. Let me show you an example from a different field. It's again, lasers allowed to do experiments and study different types of transitions and record lots of data. So let's say that here we have a transition to increase the energy of the system. You don't have spikes, but you can see here that the dynamics becomes more extreme events, more turbulent, let's say, and this is called optical turbulence, okay? And this is the data from where I showed you before. What happens if you filter out everything that is below a threshold? Okay, just analyze so we do it in the paper I'm going to show you, we did both. We analyzed the raw data as it was, and also what we call thresholded data that is shown in red. And calculated the entropy. The entropy can be calculated from a set of probabilities, and there are different ways of computing these probabilities. This is using the raw data without any filtering, and the black is a permutation entropy. This is a different way of transforming a time series into a symbols, which is called horizontal visibility graph. If anybody is interested, I can give you the details, but it's just a different symbolic rule. Basically, it's a data point. How many data points does it see? Okay? It's like thinking data points as buildings, and a high building will cover all the rest, and so on. Anyway, it's an interesting way to also transform a time series into a symbolic analysis, and you can see that the entropy decreases, which is quite strange, thinking that we're talking about the transition to turbulence, okay? And the time series I showed you before, it looks like the system becomes more chaotic, so this sounds weird. But there's also more correlations. The system becomes more correlated, and therefore some patterns start occurring more, others do not. It's less random in a way. So in that sense, the entropy goes down because there's more temporal order appearing in the system. Now, if I only calculate the threshold data, and I do the same, use the horizontal visibility graph of the permutation entropy, I see a sharp transition. This sharp transition is not seen in the other way, only by using a threshold. And of course, we have verified that changing the threshold more or less gives the same result. We surrogate the data. The simplest way to surrogate is just to shuffle the data, and this is gone. There's no transition. And the third way is to just compute the histogram of values. No symbolic analysis, no threshold, nothing. And again, here we see that the entropy decreases. Basically, this is because actually it's not so raw, but we always normalize such that eliminate the mean value and consider the standard deviation equal to 1. So basically, the idea here is that once you have extreme events, your distribution gets a tail, okay? That means that the distribution becomes more predictable because it gets like a peak, okay? So that's why basically the entropy decreases. But my message with presenting this slide is that the results can be very different depending on how you process the data and which probabilities you use to compute the entropy. And maybe if you don't use a threshold, you don't see this abrupt transition here. And you even see here that the entropy increases, and you don't see it here. So the behavior you see depends on how you look at it. OK, so we can do more with this data. Actually, it's quite interesting data. And we can see if there are some correlations changing this lag. So analyze the raw data, but instead of considering one point after another, we use a lag. And if we, just to check if there are correlations in the data, we calculate the autocorrelation function, we see a fast decay, and then there are some remaining oscillatory behavior. Here you see 3 lines. That's because we are looking at what happens right before and at the transition. So what happens here? We're trying to understand what's going on. And there are the emergence of long-range correlations during this transition. And after the transition, or before, I don't remember, is this black line. There's almost white noise there. No correlation. Now, if we calculate the permutation entropy, we see this. So basically, the permutation entropy is a nonlinear measure that allows you to amplify nonlinearities. And you can see here that there are some lags in which the system becomes more ordered. There is more order because the entropy decreases. Not too much. You can see the values are very high to the maximum, normalized to 1, the maximum possible entropy. But still, it's quite remarkable compared to the autocorrelation function. So this second plot is when we calculate the value at time y, plus a lag, plus 2 lag, compute the ordinal patterns, and calculate the permutation entropy. There are other entropies I want to mention, just in case you want to play with this. There is the range entropy, which has an extra parameter q. Of course, q cannot be 1, but it can tend to 1. And as I approaches 1, it goes to Shannon entropy. And a time series or a set of any kind is multifractal if the entropy depends really on the value of q. Okay, so that's the definition of multifractality. Most chaotic sets are multifractal. And then you can calculate, with this entropy, you can calculate what is called the information dimension. This is or a generalized dimension in which you can see how the entropy depends on this epsilon, which is the size of the bin that you use to calculate the probabilities. It's pretty much the same role as the boxes that you use to cover your object. Now we are computing probabilities. Consider the same as box counting, how many points are in each box. And this is a way to define the entropy. The dimension, a generalized dimension. So if you put q equals 0, this is basically the box counting dimension, basically, because the entropy is the logarithmic of n. And OK, so this gives you the number of occupied boxes. If you put equal to 1, then you get this becomes Shannon entropy, and this becomes what is known as information dimension. So again, calculating the entropy gives an easy way to estimate changing the size of the bin, if there's any multifractal behavior or not. OK, so I'm almost getting to the end. I think I have 10 minutes. No. See, what time? How much time? OK. All right. So let's say that we can represent a time series as a network. There are many ways to do this again. I will just present in detail one, and I will give you some references for the rest. How can you obtain a network from just a sequence of points? All right, so here's one way. You use the ordinal methodology to transform the time series into patterns. 3, 1, 2, 1, 2, 3, 1, 3, 2, and so on. And then you calculate the transition probabilities, the probability that pattern B comes after pattern A. Okay? So basically, the patterns, the possible patterns, are the nodes of the network. Here we have 6 possibilities with different colors, the yellow, the green, the blue. Okay? And it's represented, this is what it represents, is the language. What is the probability that one word appears after another? Okay? So you can see here that many of them goes to this violet, which is the trend pattern. Remember that the trend pattern tends to be very popular. If you have an oscillatory behavior, it's either going up or down. Okay? So that's the matter. That's the way to represent the time series as a network. So you have the adjacency matrix that connects 2 nodes, is the transition probability. And in each node, of course, there will be, except for the initial and final words, there will be another word coming up. So you can say that adding all those probabilities should be 1, because from this word, I have to go somewhere, okay? And this is the weight of the links. And I can also have the weight of the node, how often that node appears in the time series. And adding all these probabilities should give me 1, okay? So we have a set of probabilities in each node. These links are such that going out add to 1. And yeah?
How hard is to compare networks from different Ds?
How what?
How hard is to compare networks from the same time series by using different lengths of
Of course, you get it's different size. Because if this one is only 6, if I use D equal to 4, I will have 24 nodes.
Yes.
And 24 times 24 transition probabilities.
But
so it's very...
The time series is the same, so...
The time series is the same, you get different networks. Yes. Okay. You get different networks. Okay. But more important is that it's very difficult to go to higher order because you need to compute 24 times 24 probabilities. So you really need to have a lot of data. Typically, this is useful for D equal 3.
I don't understand what you do here, because you take 6 nodes in your network.
Yeah.
And let's say that now you've got your networks, which the nodes interact through that.
They don't interact,
I don't know yeah, I want to know how do you recover the dynamics of the system.
I'm going to show you in a minute.
Okay.
I'm going to show you in a minute. It's interesting. You get something that I think is very, very difficult to detect in a different way.
I get back to the question of Pablo. If they have detected some invariance in this...
Not that I know.
No?
Not that I know. There might be. There might be. I mean, if you consider larger networks, then you can consider that there is a link if the transition exists. Okay? So there is or there is not, and you don't put any weight, because you cannot calculate the probability of that transition, because you don't have enough data. So it's enough to see it to put a link. Okay? In this case, you can compute the probabilities of the nodes, and you can compute the probabilities of the transitions from one node to another node. Okay, so you end up with a weighted and directed network. In fact, what I talked before, this horizontal visibility graph, in that case, each data point is a node and sees the other nodes. So if you have 10,000 data points, you have 10,000 nodes, but mainly they are connected with the neighbors, because as soon as there is a high building, you cannot see the rest. Anyway, I don't have time to talk about that, but there are other ways, all right? So what you can do, you can go compute the entropy of the weights of the nodes. This is just the permutation entropy. You can compute the permutation, the entropy of each node, because you have all these links whose probability add to 1. You can also compute an asymmetric coefficient, which gives you if the dynamics is reversible, no, or is a sign of irreversibility. The transition probabilities are not the same. 0 would be a fully symmetric. 1 is when one transition exists, but it cannot go back. And let me show you what you see when you use this technique to analyze the logistic map. So this is the permutation entropy, and this is the entropy computed from the transition probabilities, from the links, okay? And you see something happening here. But nothing happens in the Lyapunov exponent because there is no bifurcation then. This doesn't detect a bifurcation. What does it detect? It detects the merging of 4 branches. See, you have 4 branches, and at a certain point, they merge. The merging of these 4 branches is not something you can detect with the Lyapunov exponent, okay? And as far as I know, I don't know any other way. Of course, it's because we are using words of d equal 4. If you use the words of d equal 3 or 5, it will detect something different. It might detect the periodic window somewhere here. I don't know. I didn't do the try. That's another hands-on exercise for you. Okay? See what happens, all right? But it's interesting because at some point here, something starts happening because this merges here, and it really has a sharp change in as seen in these indicators. Anyway, we also have used them to analyze experimental data to see if we can predict that this transition is going to happen. Here is the mean value, removing, this is from an amplifier that removes the mean value of the intensity. So that's why this is negative. You don't see any trend here. In the variance, we talk about the variance, increasing variance as an early warning indicator. You can see here that there is a small increase as you approach the transition. The permutation entropy detects us well in advance. And the node entropy, which is this way of computing the entropy using the network, it detects it even more. So it's a good indication that it's possible to detect the transition. You can also use this to classify. You analyze EEG signals, and at a certain point, the person opens the eyes, okay? So it has eyes closed over here, eyes open over here, and you can see there's some difference, but it's very tough to try to identify exactly and to differentiate the 2 states, okay? To clearly separate these 2 states. If you compute the permutation entropy, you see that when the person opens the eyes, the entropy increases a little bit, seems to become more random. And if you use these other measures, which is the asymmetric coefficient or the node entropies, the entropies of the links, looking at the transition probability, you see a smaller change. So, but the change occurs also after 1 minute that the person, of course, the data set that we analyzed, there were like 100 people, so there's a lot of variability, and it's not so far, it's not possible to fully separate these 2 states. Anyway, concluding this part, there are many methods to represent a time series as a network. I basically talked about transition network, is this one. Ordinal pattern transition network here, but there's the visibility graph, recurrence, cycles, and so on. And if anybody is interested, this adjacency matrix represents in black existing links, in white non-existing links. You can see that the structure, the time series is always the same, the x-coordinate of the Lorentz system, but the network that you obtain is quite different. And that's the problem also on time series analysis. Time series analysis extracts data, extracts information, and then you need to think what to do with it. The last very quick thing is how to represent a time series as an image, to show it, to see it in as an image, as a 2D plot, as a spatiotemporal plot. What you can do with any time series is to represent it as a matrix, okay? For that, you need to choose a particular lag and say, okay, this is a row, the next segment is the next row, the next segment is the next row, and so on. So instead of having a long string of data points, in this way, you have an image, okay? And then you plot it with color code. Depending on how you choose this tau, and I'm going back to that data that I showed you on the transition to turbulence, depending on this tau, you can have a structure with some vertical patterns here, or some diagonal like this, or alternating, you know? It all depends on how you choose your tau. It's a simple way to visualize the dynamics of a time series. It doesn't give you any quantification. It's just a way of expecting the data. If you have a periodic signal, you can have like this. If you have spikes, depends on how you represent, or black or white. This is another example of some time series that gradually becomes chaotic. You need to choose the length of the horizontal axis, and then you can see some quasi-periodic behavior with this string, or becomes more and more chaotic. So basically, finishing, there are many more methods of time series analysis. Basically, you extract information, features. All these points are different features that you get with all these methods. What to do? It's like having a radiographia and you're not feeling well, okay? So time series analysis gets this, and we can do it very well. We know how to select the wavelength of the light, the intensity of the light, focus on the right position, and so on. However, we don't know what to do with this, not doctors. Then you have to connect with the people that have the expertise. You need to go to the doctor and see, what do you see here, right? We can take the best image we can. We can use all these techniques and extract lots of features, but it's very important to go back to the people. If we are talking about the data and economic data, financial data, then you really need to go back to what does this mean, okay? So basically, this is, I'm finishing with this big data issue that we get lots of features from time series analysis, all these Fourier, fractal, probabilities, permutation entropy, whatever. You have a huge number of features, and you might have a large number of time series to analyze, so this is big data. And one thing to do, maybe some of you heard, is this dimensionality reduction. So with all this, you compress. You obtain some way of compressing the data. Otherwise, you just give all these features to a machine learning algorithm and see what you get, right? Those are basically the two possibilities that I can see you can do. The permutation entropy is an example of what we mean by dimensionality reduction, because you have 6 probabilities, or 24, or 120. These are features. But when you can compute the permutation entropy, you compress all these features into just one. If you want to put it in a 2-dimensional plane, you need another feature that is as independent as possible from this one. So suppose you have 2 features, the permutation entropy and some other feature that you obtain some way by using, there are lots of methods for dimensionality reduction. I just don't have time to talk about that, but there are many ways you can, from all these features, get them 2, which are a combination, some sort of combinations like magic, right? and you get two features, then you can do a regression, you can do some type of clustering, you can do some classification, and so on. So basically, to conclude, linear methods and nonlinear, they are all useful. They provide complementary information. They provide different features which encapsulate different properties. At any case, you need to filter what is not useful. So you get these numbers, you need to do some surrogate analysis and filter out whatever is not useful. And basically, Holger Kahn said one, and I really like this, every data set bears its own difficulties and challenges. So it's never routine. You cannot just apply blindly and see what you get. It's always look at the data first and so on. And I'm including here these references I already mentioned. The book, here's the software for you to try. This book has the software. And finally, this P-Unicorn has also implemented many of the techniques that I talk about. So this is the last exercise of the third exercise, which is play with the ordinal patterns and the logistic map, or you can use your own data to calculate the ordinal probabilities, calculate the ordinal bifurcation diagram. If you're working with the logistic map, you will see that the word 3, 2, 1 never occurs. And then you can also see how the distribution of ordinal patterns changes when you change the initial conditions. See if you get the same distribution or not, okay? Any questions? No questions? Okay, so that's it.